We're going to look at a couple more tests for infinite series and how can we tell if a particular infinite series converges or diverges. And again, we're not so much concerned with what the sum of the series is. We're just really looking at, does it converge? So the first one is called the ratio test. And so the ratio test is where we set up this ratio. So we basically take two consecutive terms, the nth term and the n plus 1 term, and we'll simplify that fraction however we can. Take the limit as n goes to infinity. If that limit is less than 1, then that tells us that the series is absolutely convergent. If the limit is greater than 1 or infinite, then the series is divergent. And then if the limit happens to equal 1, then this test is inconclusive. We can't really say one way or the other. So let's see how this works. So we have this first series, n cubed over 3 to the n. And so we would need to find the limit as n goes to infinity. Absolute value, a sub n plus 1 over a sub n. And I will ignore the absolute value because these are all positive anyway, so it doesn't really matter. So we end up with limit as n goes to infinity. We have the a sub n plus 1. So we're going to plug in n plus 1 for the n's. So we have n plus 1 cubed over 3 to the n plus 1. And then that's going to be over the an term, which is n cubed over 3 to the n. And so what's going to happen is we're going to be able to simplify this quite a bit. And the way I usually will do these is when we're dividing fractions. So I will bring this one to the numerator, flip it. So we have n plus 1 cubed over 3 to the n plus 1 times 3 to the n over n cubed. And now let's see what simplifies. So 3 to the n over 3 to the n plus 1, that is going to leave a 3 in the denominator. And then we have n plus 1 cubed over n cubed. And we can't really do much with that. We'll just write this as n cubed, n plus 1 cubed on top, n cubed here. And we could, forgot to write the limit, we could combine that and make this 1/3 times n plus 1 over n cubed. And as we take the limit to infinity, because this is also 1 plus 1 over n, and so we can see that this will go to 1 as we go to infinity. So then the limit is just going to be 1/3, and this is less than 1. So that tells us that this series absolutely converges. Okay. Let's look at the next one. We have n to the n divided by n factorial. N factorial comes up quite a bit in these types of series that we want to test this way because they're actually pretty easy to simplify. So a sub n plus 1 would be n plus 1 to the n plus 1 over n plus 1 factorial. A sub n, of course, is just n to the n over n factorial. So we want to find the limit as n goes to infinity. Again, we have only positive terms, so we don't really need to worry about the absolute value. So let's have the limit as n goes to infinity of a sub n plus 1. So n plus 1 to the n plus 1 over n plus 1 factorial times, now we'll go ahead and do the reciprocal of a sub n. So that have n factorial over n to the n. So we're dividing like we did here, but we're just going to go ahead and kind of skip that step and flip the an term. So now let's see what happens when we simplify this. So we have the limit as n goes to infinity. N plus 1 factorial on the bottom and n factorial on top. If you haven't worked with factorials in a while, n plus 1 factorial and n factorial. These are just where you multiply each the number in the factorial by every number that comes before it. So n plus 1 factorial will be n plus 1 times n minus 1 all the way down to times 3 times 2 times 1. N factorial will be n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. So the n's will cancel, the n minus 1's will cancel, and every other term will cancel except for this one, n plus 1. So n factorial over n plus 1 factorial will leave an n plus 1 on the bottom. And then let's just leave this n to the n here first. Now, if we have n plus 1 to the n plus 1 divided by n plus 1, we can write n plus 1 to the n plus 1 as n plus 1 to the n times n plus 1. That's over n plus 1 times 1 over n to the n. So now these two will cancel. And so we end up with the limit as n goes to infinity of n plus 1 over n to the n, or we could write this as 1 plus 1 over n to the n. And you might not recognize that, but maybe you do. This actually is the definition of E. And E, of course, is 2.71 approximately, which is greater than 1. So then this series diverges. All right, so then we get to the root test. And the root test, as far as the structure of it, it's going to be the same. We're going to take the nth root of the series and take the limit to infinity. If it's less than 1, then it's absolutely convergent and therefore convergent. If it's greater than 1, it diverges. If it's equal to 1, inconclusive. So basically the same principle, same rules as before. It's just now we're taking the nth root and then taking the limit to infinity. So if we're taking the nth root of this, that's really just going to get rid of the n. So we really just need to get the limit as n goes to infinity of 2n plus 3 over 3n plus 2. And the reason for that, if you had the nth root of this, the n's will cancel out, and then you're just left with this. And hopefully you can see this limit. I mean, we can divide by n if you like, but this limit will just be 2/3, and 2/3 is less than 1, which tells us that this converges. And so that's really all there is. So when you see nth power like that, the root test is a good possibility for figuring out if it converges or not. When you have a ratio like we have up here, that tells you it's probably a good idea to try the ratio test. And so these are both tools. Sometimes they work, sometimes they don't. But the more you get familiar with them, the more you will be able to try them and see if they work. And if they don't, try something else we've done before. So, okay. So if you have any questions, please let me know.